Hey guys, today we're going to be talking about connecting potential and field. So electric fields are what we learned about in chapter 20, and in this chapter, chapter 21, we've been learning about potential. Now we're going to take those two ideas and merge them together. So there's going to be two parts to this. There's going to be the qualitative and the quantitative. The qualitative part is going to involve looking at the potential lines, looking at the electric field lines, and seeing how they're related directionally. And then later we'll look at the mathematical part for how they're related quantitatively. And the big deal that you need to know, the biggest deal of this whole thing, is that the electric field at a point is perpendicular to the equipotential surface at that point. And we can look at the motivation for that real quick, or the reasoning behind it. So we know that potential is based off of a change in potential energy. It's the change in potential energy divided by the charge of whatever particle's changing potential energy is the change in potential. So it's a property of the field. And the way that we measured that was based off of potential energy and how that was changing. And potential energy is also equal to work, or change in potential energy is equal to work, which is equal to force times distance. And this force is a vector with a direction. This means that the potential energy is based on the force and its direction. So in a direction where there is no force in a specific field, so for example, if we have a field, electric field that looks like this, it's going this direction, the force from the electric field is going to be parallel to the electric field. So if you move a particle perpendicular to the electric field provides no force, so there's no change in potential energy due to the field. And these parallel lines, things that are parallel to the field, are places where the potential doesn't change, so they are equipotential. Equipotential means equal potential. So we know that equipotential lines are always going to be perpendicular to the electric field. If that doesn't make sense to you, you can just accept it as a fact. That's fine. You don't really need to know the reasoning too much, but you do need to know that an electric field at any point is perpendicular to the equipotential surface. And you can see that in their diagram here. So they've got some equipotential surfaces. Those are the green dotted lines. The electric field is perpendicular to the equipotential line at every point. So if we were going to pick over here, it would be more this way to be at a right angle with that equipotential line. And this slide basically says the same thing, but it has some good examples. So if we look at the point charge first, we already knew the electric field from a point charge, a positive point charge, points away, like you can see with these pinkish lines. They're pointing out and away. And then the equipotential lines are in concentric circles around the point charge, because we know that the potential from a point charge is V equals KQ over R. So everything with the same radius has the same potential. So those are concentric circles around the point charge. And at every point here, you can see that it is perpendicular to the tangent of those concentric circles. Now if we go over to this next example, the electric dipole, we can see the same thing in a little bit more complicated of a manner. We've got the equipotential lines, and the assumption is that equipotential lines go in certain increments. So you could say every green line is another 50 volts out, or something like that. So where the equipotential lines are really close together is where the field would be the strongest, and where they're more spread out is where the field is the weakest. And you can see everywhere on this diagram, we've got perpendicular equipotential lines and field lines. And our last example is the ever important parallel plate capacitor. So you can see here that a parallel plate capacitor has the electric field going from the positive plate to the negative plate. We've already known that. And we also knew that the equipotential surfaces in a parallel plate capacitor are like squares that are parallel to the plates, or circles if it's a parallel plate capacitor with circular discs. So those are very obviously perpendicular. And the other rule to keep in mind is that electric field points in the direction of decreasing potential. So for example, if you had two equipotential lines, this one we said was 200 volts, this one was 100 volts, and then we had another one that was 0 volts. That's supposed to be 0. The electric field would point in the direction of decreasing potential. So when you're relating field and potential and solving problems with field and potential, finding out the direction is going to be super qualitative. You're just going to have to draw a diagram, look at the picture, find the perpendiculars, figure out which way the field should be going, because these are not things we mathematically find. We will mathematically find the magnitude, but the direction is something you have to find through geometry and through thinking, but not straight through the equations I'm about to show you. So on the mathematical side, for the magnitude, we are using this equation here, which I'm going to do a quick derivation for. And when I say quick, I mean pretty quick. It's like 2 or 3 steps, I think. So we're going to start with work being the change in potential energy. This is just something that's always understood. And we know that potential is defined as delta V, change in potential, equals the change in potential energy of a particle divided by the charge of that particle. So if you rearrange that, you get delta U equals delta V, trying hard to make my U's and V's distinctive, times Q, which is the charge of a particle. So the change in potential energy of a particle is the change in potential times the charge of it. So we're just going to plug that in, a substitution over here. So the work done on a particle is equal to Q times delta V. And note, this is the work done by some entity that is moving the particle from one place to another. This is not the work done by the field. It's like if I had a particle in a field and I was pushing it with my hand, this would be the work done by my hand. And then you should also know from mechanics that work is equal to force times distance. And the force that we would be pushing with would have to be equal to the force of the electric field on the particle. And the force of an electric field on a particle is given by the equation E equals the ratio of force to charge, which says force is equal to QE. So we're going to plug that in for force over here to get work equals Q delta V, which is also equal to Q times electric field times D, QED. And the rest of this will be quite easily demonstrated. Q's divide out. If we divide by Q on each side, you get delta V equals field times distance, which is also rearranged to be the equation that I boxed earlier. Field equals change in potential over D. Now, something really, really picky that's going to screw you over if you do it wrong with this equation is knowing what this D means. So in vectors, when you're working with force times distance, the distance that you use is the straight line distance that is parallel to the force. So, for example, if these were our equipotential lines and the field is going this way, which means the force is also going that way. Okay, things are going that way. The distance has to be parallel to these lines. So if I'm looking for the potential difference or something between 2 points that are here and say here, the distance between the points is like that. that's not the distance that I'm going to use. I'm going to use only the component of that distance, or displacement, whatever, that is going parallel to the force, which is this right here. So this distance, this d right here, is going to be the distance between the equipotential lines. This is not the distance between the 2 points. In general, it is the distance between the 2 equipotential lines that the points are laying on. And that's really going to mess you up if you do it wrong. So make sure you know that this D means distance between the equipotential lines. So let's look at a couple of example problems involving both the direction and the magnitude. This question says, what are the magnitude and direction of the electric field at the dot? So when we solve these problems, the first thing you want to do is think about the directions, think about the way the field's going or the way that the equipotential lines are laying based on what you're given. So here we are given equipotential lines. And these equipotential lines are going vertically. So the field has to be perpendicular to those, which means it's going to be lying along this direction. And I'm not drawing the arrows yet because we've got to talk about which direction the arrows are supposed to go. But we know that they are perpendicular to the equipotential lines. I'm not going to draw on all the perpendiculars. So when we have equipotential lines and we're finding the field goes from high potential to low potential. And we've got the high potential over here with 200 volts, the low potential over here with 0 volts. So our field points to the left. It's going to take me a second to get the right tool to draw that in. There we go. To the left. So that's the direction of our electric field. And now we have to find the magnitude of the field at the dot. So we're going to use that equation, electric field equals change in potential over distance between the equipotential lines. So here we have a couple of options. You could do between the 2 outside equipotential lines. You could use the middle with either one of them. It's going to turn out the same. That's kind of why they're called equipotential lines. So we're going to plug some numbers into the equation. I'm going to use my outside 2 lines. So we've got our change in potential here goes from 200 to 0 or 0 to 200, whichever. Really, the sign doesn't matter here because we're going to choose direction qualitatively. So we'll do 200 minus 0 is 200 volts divided by the distance between those 2 lines, which is 2 centimeters, so 0.02 meters. 200 divided by 0.02 is 10,000, I believe. And that's volts per meter. So we know that our electric field is 10,000 volts per meter, and it's going to the left. If you want to, you can calculate it out with both sets of inner and outer lines to see that you're going to get the same answer no matter what. Now let's head on over to example number 2. This one's a little bit more complex. It's asking for the potential difference given the field. So last time we had the equipotential lines and we were looking for field. Now we have the field and we're looking for potential difference between 2 points. So the first thing we're going to do is still draw in something. This time we're drawing in the equipotential lines. I'll make them green. So our equipotential lines are perpendicular to the field. So they're going to go straight up and down because the field is going horizontally. Cool. Equipotential lines. And we don't know the potential difference between them. That's what we're finding. Oh, rip. I made up this problem. I forgot to put in a field strength. So we're going to say our field strength is going to be, let's see, 1.4 times 10 to the 5th volts per meter. Random number made up right now. All right, so to find the potential difference between 2 points, we're going to use the same equation we've been using. Field equals change in potential divided by D. D is the distance between equipotential lines, not the distance between A and B. Okay, so we're going to plug in that 1.4 times 10 to the 5th volts per meter. That's the E. That's equal to potential difference over D, which is, say it again for the kids in the back, D is the distance between equipotential lines, not the distance between A and B. So we're going to have to use a wee little bit of trig, which is our favorite. So we know the distance between A and B is 1 meter, and their displacement is at a 20-degree angle above the horizontal. So to find the distance between equipotential lines, there to there, we have to do some trig. So this side is the adjacent, and we have the hypotenuse, which means we're going to use cosine. Cosine of 20 degrees equals adjacent, which is what we're looking for, over hypotenuse, which is 1, which makes that distance D 0.9397. Okay, pretend I multiplied that over there. Okay, so we've got 1.4 times 10 to the 5th volts per meter equals delta V over, sorry, that is a V, delta V over 0.9397 meters. Multiply that out times 1.4 times 10 to the 5th gives you a delta V of 1.316 times 10 to the 1, 2, 3, 4, 5 times 10 to the 5th. Awesome. And that is going to be measured in volts. All right, so that's how you solve problems where you're given the field and you need to find potential difference between 2 points. Again, remember, D is not the distance between the 2 points, it's the distance between the 2 equipotential lines. All right, so I know that solving these can be a little bit difficult or hard to think about conceptually because it's a little bit wonky, drawing the perpendiculars, remember what to do. So in case you need a little bit of help, here is a guide for solving these problems. If you're solving for field and you have equipotential lines, you draw the field perpendicular, you draw the arrows so they go from high to low potential, and then you use your equation. If you're solving for potential difference in a field between 2 points, you have to draw the equipotential lines perpendicular to the field and make them go through your 2 points. That's the whole goal. You have to figure out what the distance between your equipotential lines is, not the points, the lines, and then calculate with that same equation. Now, before you head off, please note that on your homework in section 5, which is the section covering this material, question 3 has an error because in my late night homework typing, I forgot to give you the value for electric field. The electric field in question 3 has a magnitude of 1,200 volts per meter. So go ahead and write that down on your homework. It's also listed on the Google Classroom assignment. I'm so sorry. Please write it in. Please don't try to do it without the electric field because you're not going to end up with a numerical answer. So there's your field value. Have fun with these questions. Let me know if you need any help.